All right, friends, you guys ready to get started? Okay, you'll notice I'm not Ellie. Big surprise of this week. You all know me, I'm Andrea, the TF for this course, and today I'm going to be teaching you everything you've ever wanted to know about heat waves. So the first big question that we're going to answer is, what is a heat wave? The very simple definition is it's just unusually hot weather that lasts a few days, and you can define it relative to the normal conditions which are specific to an area. So a heat wave in Texas is going to be different than a heat wave in Alaska, for example. And the thresholds of temperature and duration, like I said, are going to vary from region to region. So that's something important to keep in mind. And these are just some images from famous heat waves that have happened recently. You can see a cute little kid having to cool off in the water. And that's kind of a fun depiction of what a heat wave can be like, but obviously it can cause some really detrimental effects. Like, for example, this is a chicken farmer who's trying to keep their poultry cool so that they don't lose their livelihood in a heat wave. We can define a heat wave either with a threshold. So for example, we can say, okay, at any temperature higher than this temperature is considered a heat wave, or we can define it in a relative way. So we can say that in the distribution of temperatures in a region, anything above, let's say, the 95th percentile is considered a heat wave. And these severe heat waves can lead to a lot of natural disasters, crop failure, or power outages. Like, for example, in Boston, we don't have a lot of built-in AC units in houses, so we use window units, which are a huge pressure on the electrical grid. And they can have some really terrible effects, especially on human health. So heat stress is a really important thing that we're going to learn about today, and how to quantify it and what it means for humans going forward. Okay, let's talk about the Siberian heat wave. So this is a heat wave that happened a few years ago, and this is north of the Arctic Circle. So this is in a region that's typically extremely cold, and they had temperatures in like the 30 degrees Celsius range, which is crazy. People were in bathing suits. And different analyses of this event claim that climate change made this heat wave 600 times more likely. But that's kind of a complicated thing to say very broadly like this, so we're going to dig into what exactly that means and how to quantify statistics like that. This event caused huge forest fires. That's what we're seeing on the top right. And this is a temperature map of the temperature anomaly during this heat wave in Bokryansk, which is where this heat wave occurred. So you can see that there's like a 7-8 degrees Celsius temperature anomaly in this region, which is huge for that area. And then this is another representation kind of the same thing. So what I'm showing here is the black line that isn't wiggly, that's kind of more straight, is just the average temperature on that day across 1980 to 2010. So that's like the climatology of that region. And then the wiggly line is showing what the actual temperature was during this year when the heat wave happened. And you can see it circled in the red circle is this heat wave. So you see a huge temperature excursion above the mean, and that's what we're quantifying as a heat wave. And you can see it lasted a really long time, and there were a lot of big temperature spikes during that time too. Okay, so classic to this class, we're going to watch a cute little video that will show you the devastation during this record heat wave. So clearly, these heat waves are more than just you being sweaty for a day and having to go take a plunge into the pool. And there's a lot of places on Earth that don't have the infrastructure, even including in the US, to deal with this kind of thing. So now let's move a little closer to home. We have had examples of these really dramatic heat waves here in the US. So this is an example of a heat wave that occurred near like Washington, Oregon on the Pacific Northwest. And some of you probably remember it. I have family in Seattle, and none of them have air conditioners, and it was a really intense event, and it kind of makes it more real to you when it's happening this close to you. And basically the most dramatic effect of this is this huge spike in the death toll. This has happened in Washington and in Oregon, and you can see that compared to kind of the average death tolls earlier in the year, there was a huge spike during the heat wave. And this is a similar plot. This is showing that these are heat-related emergency department visits, so a huge spike. People basically facing heat exhaustion because they couldn't cool off effectively in these conditions. And about 600 more people died during this event than they probably would have in a more normal climatological event. And because these are so dramatic and we see such huge increases in death tolls during these events, heat waves show up a lot in the news, and their connection to climate change seems pretty straightforward. For example, the news tends to say that in a warmer climate, we're going to have longer, more frequent, and more dangerous heat waves. We see them saying climate change makes heat waves more frequent. And also people tend to say things like, oh, we're going to see a tenfold increase in this type of event because of climate change. And a really big part of today is us trying to understand exactly what that means and whether they're talking about frequency or they're talking about severity, and those are things that are very important. And we're also going to try to understand the mechanisms behind heat waves and how they occur and how climate change is going to make them more dramatic. I thought this was a really interesting plot. This was published in the New York Times. So on the left, what they're showing is a histogram of average temperatures from 1950 to 1980. So this is like a pre-industrial situation. And you can see it looks a lot like a bell curve. It's pretty concentrated in normal temperatures, but we have those extreme events on the left in the cold and on the right in the hot. But those events don't happen very often. And then they compare that data set to the temperature histogram from 2005 to 2015, and you should notice two things. First, the curve shifted to the right, so now we're seeing kind of like a shift of the mean in these temperatures. But you can also see that the bell curve itself changed shape. It got a little bit squatter, and so we're getting more events in those extremes, but the mean itself is also shifted. And this is what just looking at this plot makes you think, but we're going to kind of dissect it, and this is clearly a cartoon, and so whether or not it's representative of what's actually happening, we'll get into. Okay, these are our goals for today. First, we want to understand the mechanisms of the heat waves. We're going to go through all the different atmospheric phenomenon that can cause heat waves, but also exacerbate heat waves. And then we're going to spend some time talking about health effects and why warm and very moist conditions are very difficult for the human body. And then finally, we're going to talk about interpreting these heat wave statistics that are shown so much in the news and how to think about that in a changing climate that is getting warmer. But before we do that, open your workshops. You are going to make the plot that shows this Siberian heat wave that we talked about earlier. Hopefully you are approaching a figure that looks like this, if you have not already gotten a figure that looks like this. And what we're plotting here is the climatology, which, as we painfully discovered, is the average temperature on a specific day averaged across many years. So we had this data set that was 40 years long, and we looped through it. We found every October 1st, for example, and then we averaged over every October 1st in that data set to get the average temperature on October 1st. That's the climatology. We do that for every day of the year. And this provides a baseline for what the average climate looks like over a year. And this captures things like the seasonal cycle, which are important. And that's information that's lost if we just average over every single temperature value. And then on top of this, we're plotting the actual temperature trend in Verdansk during this time. And you can see that there are huge excursions from the mean. And when I say excursions from the mean, I just mean that the temperature is different than the average temperature on that day over the last 40 years. So for example, we see this huge increase in temperature. It's much higher than the average temperature during this time, and it lasts for a really long time. And we see this a few times during this year. And where would you say a heat wave has occurred based off of this plot? That one? Nice, I agree. Hopefully this makes more sense now that we see this beautiful plot before us. All right, now we're gonna figure out the mechanisms for a heat wave. And there's a lot of them. They're not all connected, and not all of them cause heat waves necessarily. They more amplify heat waves, but we're gonna go through a bunch of them together. And I really encourage you to ask me questions as I go through this. Okay, number one, mechanisms of heat waves. Number one, I'm going to put high pressure aloft. This won't make sense at first, but we're going to dive into it. Will lead to subsidence and warming. So I want you to reach back into your brains to when we talked about hurricanes. And we're talking about low pressure systems and how that leads to different wind formations. This is very similar. It's kind of the opposite scenario. So we have a high pressure system with anomalously high temperature in the middle, and then outside it's lower temperature. What direction does the pressure force want to go? Right, high to low, great. Okay, do you guys remember what geostrophic balance is and how it relates to the pressure force? No? This is a good concept that I have had to learn many a time in my grad student career. What geostrophic balance is it says that the Coriolis force has to balance the pressure force. It's pretty much that simple. So we know this is the pressure force. I'm also going to use, which means that the Coriolis force has to balance it in this direction. Let's pretend that we're in the northern hemisphere. What direction does the Coriolis force want to turn the wind? Left or right?
Left.
We have left. Anyone agree or disagree?
Does it depend on the hemisphere?
Yeah, so we're in the northern hemisphere.
Right.
Right, great. So this is the wind in this case. And because there's friction or whatever, it doesn't point perfectly perpendicular so that it's just kind of spinning in a circle. There's some component of it that's pointing a little bit outwards. Based off of the direction of this wind, are we going to have mass flow in to the high pressure system or out of the high pressure system? Based off the direction the wind is blowing. Out, right. But we know that mass can't just go away, right? We need something to balance this mass that's leaving the high pressure system, which means that we need, so we have mass going out, which means that we need to pull mass from up in the atmosphere down into the high pressure system to keep the total amount of mass balanced. Everyone with me so far? Great, okay. So now we're pulling mass from very high down. So the air that's coming from up here is cold, right? Because it's higher up in the atmosphere. We know that temperature decreases as you go up. But now we're pulling it down. We're pulling it down adiabatically, which means that its energy is conserved. Let's pretend like it's pretty dry, so it's not going to undergo any phase changes. It has to conserve dry static energy. I don't know if we've specifically talked about dry static energy yet, but it's pretty similar to moist static energy. We just dropped the term that has to do with moisture. That's it, because we're assuming nothing changes moisture-wise on either side of the equation. So we're going to conserve dry static energy. Who remembers the first term in this equation? Has to do with just temperature. Okay, the first, oh yeah, let's hear it.
CPT.
Yes, CPT. This is the internal energy that the parcel has just because it has temperature. We're going to assume no moisture, so the term with the latent heat is not in it. What's the last term in this?
Q star. Like Q star.
Yeah, typically we have the Q star, but because we're doing dry static energy, we're ignoring any moisture terms.
GZ.
GZ, right. This is the potential energy. Okay, so we're going to assume that the dry static energy has to be conserved as the air is coming down. That's called subsidence. It's subsiding air. And as it's going down, what's happening to Z? Is it going up or down? Down, right. So in order for DSC to be conserved, what has to happen to temperature?
Goes up.
Exactly. So we're bringing the parcel down. It's getting warmer. Yeah.
Can you repeat what GZ is?
Yeah, so this is gravity times Z, which is height in the atmosphere. It's essentially potential energy. So what dry static energy and moist static energy does, it just adds together the different types of energy that this parcel has. So this is just the internal energy, the fact that it has temperature and its molecules are moving around. This is the potential energy. And then the LQ term is like the potential energy you can get from evaporating or condensing the moisture, because you have to use latent heat to do that. Yeah.
And why is GZ going down?
Because we're pulling air. We're talking about the air parcel that's coming down because of the high pressure system doing subsidence. Great questions. More? Okay. The bottom line is the temperature of the air that's subsiding is going to increase. And that's not good, right? Because we're pretty much warming up air and then bringing it close to the surface. That's one way that this could cause a heat wave, is just because of this heating, because we're subsiding the air. But there's another effect too, where, I'm going to call this 2. Warming equals lowering of relative humidity. That's what I'm going to call this one. Okay, who remembers the definition of relative humidity?
It's the amount of moisture currently in the air parcel divided by the maximum amount of moisture the air parcel can hold.
Perfect, yes. So that's Q divided by Q star, and Q star depends on temperature, right? Like I said, we're gonna pretend like the moisture content of the parcel doesn't actually change as it's moving. It's not gonna condense anything out or gain any moisture at all. But because it's moving down, what's happening to the temperature? Temperature is increasing, right? So what's gonna happen to the saturation vapor pressure, which is how much moisture it could hold as we increase the temperature? What holds air better, or what holds moisture better, warm air or cold air? Warm air, right. So the amount of moisture it could hold is going to increase, but the actual amount of moisture it has isn't going to change at all. So what's going to happen to the relative humidity? Decrease, right. So this is going to cause like a drying effect. Drying, I think, is misleading because we're not actually losing any moisture. It's just that the relative humidity of the parcel is decreasing. And if we're decreasing the relative humidity, that's going to mean that no clouds are going to form. So we have a very low relative humidity. It's very hard to saturate this parcel, which means we're pretty much going to form no clouds. What happens to the surface temperature if you take all the clouds away? Goes up, right. So this is just amplifying the fact that we've already brought really warm air to the surface, and now we're getting rid of all the clouds. So that's going to mean surface temperature increases. So now we've got two ways. Surface temperature is increasing, and we're not even done yet. OK, so these are how it directly affects temperature. But having this high pressure system in the way can also just affect the weather of what's going to happen in the system. So I'm going to write here, high pressure diverts rain. So if you have a rainstorm that's supposed to come in here, it's going to be deflected by the high pressure system. And so now we're losing out on rain that could have hit the system. And that's going to make the soil much drier, for example. And so this is going to equal dry soil. And if you have dry soil, then the soil can't cool itself off by evaporating water out of it. So dry soil, and that's less, I'm going to call it evaporative cooling. And that is going to increase the temperature of the soil. So, indirect way that it leads to an increase in temperature. OK. We're still not done. OK, 4. Yeah.
What is that high pressure like coming from in this situation?
In this case, it happens a little randomly. Like it's just that you have weather and you get these little high pressure systems. And the point is that it exacerbates itself and turns into
it's
this.
It's like a positive feedback.
Yeah. Would you say that's true? Yeah. Okay. Okay, 4. Clear sky. Increases long wave cooling, which increases subsidence. This one was a little more subtle to me, so I'm happy to spend a little bit more time on this one. OK, so I want you to imagine we have a cloud, and here we have no cloud. And in both cases, we have a parcel of air. And the parcel has temperature, and so it's trying to emit long-wave radiation. Okay, we've talked a lot about how clouds have a very strong shortwave effect. They block sunlight from getting to the surface. But clouds are also made out of liquid water droplets, and those are extremely good long-wave absorbers. So it's a very strong greenhouse effect. So this long wave that the parcel is trying to emit so it can cool is just going to get reflected right back to it, and it won't be able to cool. So it'll be warm. Okay. Versus here, there's no cloud. So this parcel is able to cool itself off. There's nothing reflecting any of the heat back to it. And this will make it cold, or colder than its environment, which means it'll be more dense than its environment. Does that make sense to everyone? Yeah? Okay. And if it's more dense than its surroundings, then it's going to sink. we're on to 5. We're almost there, you guys. Thanks for hanging in. Okay. Subsidence is also going to decrease convection. I'll tell you why in a sec. Which is going to lead to weaker surface winds. And that is going to decrease evaporative cooling as well. Okay. I just put a lot of things on the board. Let's break it down. Okay, so typically in the atmosphere, this is Z and this is, I'm going to write V. It just means like the velocity of the winds. Typically it looks something like this, where you have like much stronger winds up top because there's no friction up there, and then they kind of decrease towards the surface. But we do have surface winds. And the way that the momentum from higher up in the atmosphere gets transferred to the surface is through convection. So this is convection. So we're moving this air around through convection, and that's transferring the momentum from higher up in the atmosphere where we have really strong winds to the surface. Okay, so we're getting surface winds, and that's really good because if you guys remember from our wow, it was really far back, our hurricanes unit, we talked about how evaporation is tied to the velocity. Oh, wait. Oh, no, I'm forgetting. Okay, something like this. The transfer of moisture from the surface up into the atmosphere, the evaporation of it, has a lot to do with how fast the wind is blowing. And that's because if you have completely still air, you're going to evaporate a little bit into the air right above the soil, and it's going to get saturated, and then you're not going to be able to put any more moisture into it. So the wind is really important to kind of blow away that air, so it's new air that you can evaporate more stuff into. So this is great. The convection brings the surface winds down, and that means we can evaporate more stuff, which means we can cool off the soil because we're doing a lot of evaporation. But that gets kind of messed up when there's a lot of subsidence going on. So essentially what's happening with subsidence is that we're bringing all of this warm air down. And so the temperature profile wants to, here, let me draw it. This is temperature as a function of height. The temperature profile wants to look like this, which is just decreasing as it goes up. But because we have all of this warm air being brought on top, it might start to look something like this. This is called a temperature inversion. It's called that because it's just the opposite of what we expect. And this, you can see here that temperature is increasing with height as we go up. And this means that we've got hot stuff above cold stuff. And we know from experience that cold air doesn't like to move up into hot air. It's usually the other way around, right? Hot air rises. And this is a very difficult situation to have convection in. It's just very hard to get things going. We've pretty much turned off convection. It's very difficult to move cold air upwards. And so without the convection, this momentum from the upper winds can't get communicated to the surface. So we've essentially turned off the wind at the surface. And this means that very little evaporation can happen and very little evaporative cooling can happen. So this will once again increase temperature because we've decreased evaporative cooling. Okay, I've only got one more for you. The last way, well, not the last, I'm sure there are a million other ways, but the last one that we're going to talk about is if, let's say, here is our heat wave. This is the equator. If we have winds bringing air, this is kind of separate from all of these, so I guess it's fitting that it's over here. This is just another way heat waves can happen, is if all of a sudden you have a bunch of wind coming from the equator, then that's going to bring the warm air from the equator up into this area that is normally not that warm, and that can also cause a heat wave. So I'm going to call them southerly winds. Yeah. I've always found this notation of southerly and northerly very confusing. Southerly means from the south, not blowing to the south. That has always confused me, so I didn't want it to confuse you. Southerly means from the south. Southerly winds coming in, they're warmer. It's going to warm up that area. Okay, I just threw a lot of information at you. More questions? We're going to see some examples in a sec. Okay, I'm going to move on, but we can always come back to this if more questions arise. Okay, mechanisms of heat waves. Who thinks that they can provide 10-second summary of why subsidence happens with high pressure anomalies? And the answer is on the board and on the slides, so the stakes are low. Yes?
So in a high pressure system, the winds are blowing mass outward, so there needs to be mass coming in to compensate. So wind is or air is falling down, or like being sucked down. And as you're losing gravitational potential energy, the temperature needs to increase for there to be conservation of energy. So the temperature increases.
Perfect. Yes. Great. Okay, so this slide is just demonstrating exactly what we just talked about. Here we've got some pictures much better than I can draw because everyone knows I'm not an artist. Okay, so this is the classic example from like hurricanes, right? We talked about week 2. Low pressure system, the balance of the pressure force and the Coriolis force causes this inward spiral of air, and that causes, because of mass conservation, you've got all this air coming in, you've got to shoot some up off the top, otherwise mass is not going to work out because of physics. So this is the classic hurricane scenario. What we're talking about here is the opposite. High pressure system, air is leaving, so air has to come in through the top, convergence, warming. Here's a little diagram if you like vector diagrams. Okay, more mechanisms of heat waves. Does anyone want to attempt why relative humidity decreases and how that relates to cloud formation and therefore shortwave forcing at the surface? Yeah.
So as the parcel of air is going down, the temperature is increasing, which means that the saturation humidity is increasing. And since saturation humidity is in the denominator of relative humidity is going down, and that means that it's drier, which means that there's not going to be as much cloud formation.
Yeah, perfect. Right, and then more sunlight can get to the surface. Great. Does anyone want to give the radiative cooling argument a shot? That one was the hardest for me, I think. Yeah.
So there's a parcel of air in a cloudy sky. If it wants to cool down, it'll try to emit long-wave radiation, but then it will just get bounced back, and so it won't be able to cool. But if it's got a clear sky, then it'll just emit the long-wave radiation, and then it'll cool down, and then it'll become more dense with a sink, which leads to increased surfaces.
Yeah, perfect. You guys are killing it. I'm so proud. Okay, how does this lack of precipitation from diverting the storms lead to a warmer surface in the long run?
Since there's less precipitation, we have much drier soil, so there isn't evaporation, which leads to the cooling of the soil, so it can't release that heat and it stays warmer.
Right. Okay, the surface winds one is pretty straightforward. We're bringing warm air from lower latitudes. Okay, does anyone want to try the convection one?
Subsidence means that you have like a stable temperature profile, so you have warmer air above colder air. So that means that convection, which happens when there's circulation between the surface and altitude, can't happen anymore. And because of that, you're not getting the transfer of momentum from the upper atmosphere toward the surface. And so surface winds are decreased. And lower surface winds means less evaporation, so less evaporative cooling.
Perfect. All right, you guys are experts on heat waves now. We know it sucks when it's hot, but why does it actually matter? How hot it is, but also how humid it is. And someone asked a really good question, I think it was Lex, what the relative humidity actually means and why it's important specifically for humans. And that's what we're going to talk about here. So we're going to talk about heat stress, which is the thing that leads to heat exhaustion, or in really severe cases, heat stroke. And this is because our bodies operate at a very specific temperature, and our body doesn't like to be warmer than that. I think our proteins start breaking down or whatever. It gets very bad. I'm not a biologist, but something about it, we need to be at the right temperature. And how hot it is outside will affect our body's ability to maintain that temperature. So here's some statistics. As climate change has progressed, almost 8,000 people have died from heat-related causes, which is about 600 per year. And they refer to this heat stroke and heat exhaustion as a silent killer because it's not as dramatic as hurricanes, which will rip your roof off of your house, or sea level rise, which you'll see devour Louisiana. This is something that just happens on an individual level. But it's important that we understand how it works. Okay, so I'm gonna do a little bit more board work. I'll stay over here just to keep that up in case people didn't get time to write it down. We're going to talk about heat stress. Okay. I'm going to read to you what the definition of the wet bulb temperature is. To me, it makes not that much sense, so I'm going to read it. You will agree with me that it's not super easy to understand, and then we're going to break it down. The wet bulb temperature is the temperature a parcel can achieve if it is adiabatically cooled to 100 degrees relative humidity, or 100% relative humidity, by evaporating water into it where latent heat is taken from the parcel itself. How confident do you feel in wet bulb temperature? Not me. Okay. I like to think of it in a more human way because we see examples of it every day. What is like the first thing your body will do if you get too hot? Sweat. Right. Why does sweating work? Yeah, sweating cools us down. Why does it cool us down?
Evaporative.
Exactly. But you'll notice, I'm from Texas. It's very hot there. It's super humid. I would say that living in Texas is way worse than living in Arizona. And that's because Texas is really humid and Arizona has very dry heat. And so you hear that a lot. People say, oh yeah, it's really hot, but it's a dry heat. And so why does that make it more bearable? That's what we're going to talk about. Okay, you're about to see my really good artistic abilities. That's an arm. This is why I'm a scientist. And it's really hot, and so we start sweating. That's water droplets. So we're going to pretend there's no wind. So it's like stagnant air that's on top of us. Our body's temperature is going to be like equilibrated with the temperature around us. So this is the air around our arm. This air has some temperature, T, and the air also has a relative humidity. And we are going to evaporate these droplets into this air, which will raise the relative humidity. But in doing so, we are going to decrease the temperature because we're using latent heat from this system in order to do this evaporation. So it's like an internal evaporation that's happening. And we are going to conserve energy. So let's think about our different types of energy the way we talked about dry static energy. A hint is that we are considering moisture in this case, but we're going to pretend it's all happening on the ground, so don't worry about potential energy. Okay, so what is the first type of energy that something has? Heat. Yeah, it has a temperature, it has internal energy. So we're going to say CPT. This is the internal energy, just because it has a temperature. Okay, what's another type of energy that it has? Right, okay, so it has potential energy, but we're going to say this is all happening at z equals 0 at the surface. Or anyway, we're not going to change where we are, so that doesn't matter. But yes, that is right. Another type of energy. This is the one that was missing from the dry static energy equation that we normally use. Oop. I heard a Q star. I like the sound of that. Yes, we also have our moisture. Okay. The thing to be careful of here is that Q isn't necessarily the saturation moisture. It's just actually how much moisture is in the system. And you'll notice that I didn't tell you how much moisture is in the system, but I did tell you what the relative humidity was, so we can back out. So we know, for example, that relative humidity is equal to Q over Q star of T. So I can write this a little differently by subbing in for Q, relative humidity in Q star. So this is the energy that our arm and the air above it has when we start to sweat. Okay. We're going to define a new type of temperature, which is called the wet bulb temperature. And this is the temperature that our body and the system can achieve if we evaporate all this sweat up into this air until the air becomes saturated. That's going to be the limit of how much we can evaporate the moisture into that air. So we want the energy to be conserved because energy can't be created or destroyed. But we're just going to move to a new temperature and a new moisture content because we're evaporating. So I'm going to define this new temperature as the wet bulb temperature. I'm going to put a little subscript W on it for wet bulb. So this is now the new internal energy that it has, but it's also going to have a new moisture amount. It's now going to be saturated because this is the most moisture that we can like put into it.
RH is just 1.
Yeah, RH is 1, exactly. So I can write Q star, but what temperature am I putting in here now? TW, exactly. Okay. So what we're saying here is, okay, we have the actual temperature of the air. Let's say it's 70 degrees out. And the actual relative humidity of the air. But that doesn't really tell us a lot in terms of, as a human, what it feels like to be in that environment. What we really care about is what is the minimum temperature that we can achieve by sweating. That's what we actually care about, and that's what the wet bulb temperature is. Okay. And you'll notice, if the relative humidity of outside is equal to 1, then what is the temperature equal to?
TW.
TW, right. And so in a world where, let's say, there's a lot of moisture in the air, that's why when it's really humid, it feels so much hotter than it would if it weren't very humid. It's because it's inhibiting your body's ability to dump heat. Okay, great. Okay, yeah, this is essentially what I just said. If the relative humidity is higher, then the wet bulb temperature will also be higher. And that means that your body cannot cool itself as effectively as it would have in a drier environment. Like I said, if the relative humidity is 100%, then the temperature is the same as the wet bulb temperature. And an important thing to keep in mind is that in the current climate, the wet bulb temperature is about 31 degrees Celsius. To compare, the human body is like 37 degrees Celsius. So like this is a comfortable, I think this is around like 87 degrees-ish Fahrenheit. But if we're exposed to wet bulb temperatures that are greater than about 35 degrees Celsius, that's going to get bad for us. And the reason is because the body has a lot of internal mechanisms to produce heat. So even if the outside temperature is the same as our internal temperature, that's still not very good for us. We need a little bit of wiggle room there. This is the equation that I just wrote on the board, but there it is clearer if you couldn't see it. And then this is a really interesting plot. So what I'm showing here is the relative humidity and the temperature. And the color is showing what the wet bulb temperature is, corresponding to this relative humidity and this temperature. So let's say it was 40 degrees Celsius outside. That's pretty hot. And then if you increase the relative humidity, see, you can notice that the wet bulb temperature is always a little bit less than, because you can evaporatively cool and whatever. But as you increase the relative humidity, you warm up the wet bulb temperature, which means that your body can't cool itself off as effectively. So the main relationship to look at here is that increasing relative humidity increases the wet bulb temperature, and that's bad. Because the wet bulb temperature is the minimum temperature your body can achieve by sweating. So you want that to be low so that you can cool yourself off. Okay. And then also, of course, as we warm the earth, let's say we're going to assume that the relative humidity is always going to be 60%. As you increase the temperature, you also increase the wet bulb temperature, which makes sense. It's getting warmer out, so your body can't cool as effectively in that direction too. Okay. So this is something that we are very worried about, because this is how all the heat deaths happen, is because of this effect. Okay, workshop 2. Okay, so now we want to talk about trying to understand these statistics that people cite in the media when they're talking about heat waves. And a lot of you have already asked a lot of good questions about like whether just shifting the mean is what's going on, or if there's a change in dynamics of the atmosphere, and we're going to get into all that here. I think that there's a lot of attempts in the media to attribute things to climate change. So for example, they'll say things like, human-caused climate change made this heat wave 10 times more likely. And really understanding what that means and how they came to that conclusion, I think is really important if we want to be critical climate change thinkers. Or they'll say something that isn't quite the same, but similar, as the same event would have been 2 degrees less hot if in a world that was 1.2 degrees cooler. And trying to understand the difference between saying those two things. Not to say that either of them are wrong, but they mean different things. Okay, so this is something that you'll end up doing in your notebook, but what we're showing here is basically we ran a bunch of different models, and we're showing their seasonal cycle, and then we took the mean. And so this is in a pre-climate change simulation, and you can see that like the mean, there's like a few times when we have examples where we have temperatures above the mean. But none of the temperatures really exceed about 40 degrees Celsius. And then we ran the model in an RCP 8.5 scenario, which is like the worst scenario. And you can see now the mean is hitting this 40-degree mark. So before, even our worst, most extreme events were barely making 40, and now we have the mean hitting 40, and so the events above are even worse. And so clearly we're expecting that these events are going to change as we experience climate change. But understanding the statistics of what's going on is what we're going to talk about here. So the blue curve is the bell curve for temperatures. It's like a histogram of temperature. And so you can see that it's a pretty narrow peak. Mostly it's just kind of average temperatures, not too hot, not too cold. But then we have some extremes on the left and right. Okay, so that would be like for one type of atmosphere. Let's say the atmosphere moves a little differently such that we have more extreme events in general. The bell curve is going to be a little bit squatter. The standard distribution, or the standard deviation is going to be bigger. And so you're going to have more of these extreme events. That's two different types of atmospheres. Okay, now we're going to warm up the planet. There are two things that could happen. We could either take this initial bell curve and just shift the mean. And of course, that's going to lead to more. So we defined anything here as a really extreme event. So of course, now we're experiencing more of those extreme events. And that would be just if we shifted the mean. But let's say we both shifted the mean, but we also changed the way that the atmosphere moves. That's the red curve. That's going to mean not only are we having more events, we're having like a much more high extreme event probability. You guys with me so far? Okay. So trying to understand in our projections of climate change, are we just going to increase the temperature and shift the mean, or are the dynamics of the atmosphere actually fundamentally going to change, which will lead to things like, for example, more high pressure systems that cause the heat waves, et cetera. This is something you will also be plotting in your notebooks. So what I'm showing here is the probability distribution function. You can kind of think of it as the little bell curve that we were looking at. And I'm showing it in the pre-industrial case, so that's the blue, and then in the projected, like we modeled this in the RCP 8.5 scenario, that's the like salmon colored one. And then this green one is an artificial one that we made where we just shifted the mean of the blue one. And we're trying to demonstrate that based off of our current climate models, it does kind of seem like it's going to be more of a shift of the mean versus a complete change in the dynamics. Of course, we do have a little bit of deviation. So that's one way of looking at this, but that's not always the most helpful. We also are interested in things like the duration of these events. And so maybe we'll have a really hot day or two, but that's not nearly as dangerous as if we're having half a month of these kind of conditions. So what we're plotting here is from the same two data sets, but we're plotting the duration of these events. So in the pre-industrial case, we have most of the events happening for a duration of less than 5 days. But you can see that in the warmed scenario, that distribution really spreads out. And now we're having events that last upwards of 15 days. And then this green line is, again, the simulation where we just shifted the mean. And so you can see it agrees pretty well with what the climate models are predicting. And then finally, what this is showing is the maximum temperature during these events. In the pre-industrial case, we have our maximum temperatures during the heat waves of about 40 degrees Celsius, which is similar to what we saw in the really messy lines that we were looking at on the last slide. And then as we warm the planet, we're seeing temperatures upwards of 47.5 degrees Celsius. And again, it agrees pretty well with this shifted mean scenario. So that's what makes us think that, based off of our current climate models, that we're expecting this to be more of a shift of the mean effect and less of a complete change of the atmospheric dynamics. Now we're going to get into the two different types of talking about heat wave statistics. This is called a CDF. It's a cumulative distribution function. Basically, it's the integral of the PDF. And the way to read it is if you take an event here, so let's say this has a value of 0.99, that means that the temperature is below this value 99% of the time. Okay? So the temperature is above this value only 1% of the time. Versus here, the temperature is lower than this about 60% of the time. The temperature is higher than it about 40% of the time. So that's the way to read a CDF. How many of you have seen a CDF before? Okay, a few of you, but not everyone. The people who've never seen it before, does that make sense? Okay, and so in the warmed case, you can see that an event that only had okay, we're going to call it an event like the 40 degree temperature. It was colder than 40 degrees 99.9999% of the time. Versus in the warm scenario, it's only colder than 40 degrees like 95% of the time or something. And so this is the reason why the CDF is helpful to look at. Okay, this is exactly what I just said. An event that in the pre-industrial case was warmer than 99.9% of the days is now only warmer than 95% of the days. And this is because we've shifted the mean. And so therefore, it's much more likely to happen. Okay, so that's one way of thinking about it. But there's another way of thinking about it that, okay, if the mean okay, I'm going to actually draw this because this was confusing to me. This was our initial curve. We warmed the climate. All we did was shift the mean. I'm going to call this 40 degrees. And this, I'm making up numbers, 30 degrees. In the warmed, or no, I'm going to call this 37 degrees. Let's say we shifted the mean 3 degrees. In the warmed scenario, which is the blue line, it being 40 degrees has the same probability as it being 37 degrees in the pre-industrial scenario. And that's shifted by the mean. That's what we mean here. Okay. Now we're breaking down these two ways. We're going to do a tiny bit of math. So one way to think about it is saying, okay, the heat wave that just occurred now is 10 times more likely because of climate change. And so that's kind of looking at this CDF. Okay, so I'm calling this heat wave statistics. Okay, one way to think about it is a change in frequency for a given temperature of an event. So for example, let's say in the pre-industrial case, this is our CDF. It looks like this. This event here was warmer than 0.9999 of the other events. So this event, anything warmer than that, only happens like 0.01% of the time. Okay. But we can also use this to think about how often an event like this will happen. This event will only happen 0.001 times. But if we're talking about percent, it would be 0.01. Bear with me. Okay. So let's think about, for example, per decade, how many times is this event going to happen? So what we can do is do 365 times 10. I'm doing it in units of days because these measurements were taken daily. So this is a decade. And it's only going to happen 0.0001. So per decade, this event is going to happen 0.365 times. Or if we put that in years, every like 27.4 years. So this extreme event in the pre-industrial case only happens every 27.4 years. So not very often. Okay, but now we're going to go to the warmed climate scenario. This is a little dramatic. But now let's say instead of 0.9999, it's only 0.999. How often is this event going to happen? We're shifting in order of magnitude. 2? I heard 2? Yeah. This event's going to happen every 2.74 years. So this is what they mean when they say, oh, this event was 10 times more likely to happen because of climate change. What they mean is an event of this temperature, this magnitude, is 10 times more likely to happen because its return time is 10 times smaller. Does that make sense? This is days per decade. Okay, so that's one way to think about climate change statistics. Another way to think about it is take an event of a given frequency, of like a given likelihood, and what is the change in magnitude of that event. So let's say we're going to take an event that, let's say, only happens every 30 years. And now we're going to say, okay, how warm is an event that only happens every 30 years, but in a warmed climate? You see what I mean? Okay, let's write that out. So this is change in magnitude, or I'll put change in t to be clear, for a given frequency. Okay, so this is the first one we talked about. This is a change in frequency for a given temperature. And so what we're showing here is our CDF, and we're comparing the blue with the purple lines. And clearly, an event of the same temperature is more likely to happen in a warmer climate. And so if in the pre-industrial case, a 40 degrees Celsius heat wave only happened every 30 years, it's now going to happen about every 3 years. That's what they mean in the media when they say this event was 10 times more likely to occur due to climate change. And what this is showing on the right is how the maximum temperature varies with return time. So you can see that like more extreme events with higher temperatures don't happen as often. And that's kind of just a nature of the bell curve. They're very extreme events. They're very unlikely to happen. And then the second one that I just introduced is now we're taking two events of the same frequency and comparing the difference in temperature of those two events now. So now, essentially on the CDF, I'm looking at like some magnitude of the CDF and comparing it to the same magnitude in the pre-industrial case, and what is the temperature difference between those two. And so this is slightly different. So I'm saying, okay, I want to look on the CDF for a value of 0.9999. And in the pre-industrial case, that corresponded to a temperature of 42 degrees. But in the warmed climate, where we've shifted the mean by 3 degrees, the same frequency of event, or an event that had the same probability of happening, is now 3 degrees warmer because we've shifted the mean of the bell curve. Yeah.
So is it like one is moving along the y-axis and the
Exactly. That's a great way to think about it. Yeah. Okay. And so I think it's good to keep these two things straight because when you're reading media about heat waves, I think it's pretty well settled that heat waves are going to become more frequent, but really understanding when they're saying statistics exactly what they're talking about, I think is very important. Okay. These are just some future projections from some climate models in the Great Plains area. And so kind of exactly what we were discussing, the number of days per year that we're expected to have a heat wave going on during those days is going to increase. We're also expecting the maximum temperature of those heat waves to increase, the duration, as well as the number of events per year. So we're expecting kind of a lot of these things to happen at once. I'm going to intro this because you're going to have to do a workshop about this, but essentially these maps that I've been showing you of like the pressure anomaly at the surface and how that corresponds to the temperature anomaly and all of those things, and also the winds, you're going to be choosing the place where you grew up, and you're going to be looking for heat waves and making these maps yourself. So that'll be interesting for you, but these are kind of the maps that you're going to be making. Okay, and then just to wrap it up, these are the observations and projections of heat waves. And I think the thing that's most interesting to me, and that I don't understand super well, but I think is interesting, is, so here what I'm showing is the increase in the temperature of a heat wave versus how much the Earth as a whole has warmed. So in like a perfect we shifted the mean scenario, you would expect that the heat wave will become 3 degrees warmer if we shifted the mean by 3 degrees. But that's not totally what we're seeing. So you can see here that for a 3-degree warming above pre-industrial levels, we're seeing maybe like a 3.5 degree increase in the heat wave intensity. And it becomes a little bit more dramatic when you get to higher temperatures. So maybe we expect 5 degrees of increase in the heat wave intensity for a 4-degree increase in the global average temperature. And so I think that's interesting. Not super dramatic, but not good nonetheless. Yeah, event intensity is increasing slightly more than the global mean. Okay, and lastly, you remember what we showed you in the very beginning, this image from the New York Times, which is showing the bell curve in the pre-industrial era, and then the bell curve compared to what's going on now. And you'll know this is actually using real data showing it. And you'll see that, it's a great graphic, but I think we can healthily criticize that it seems like they dramatize the change in shape of the bell curve as well as the shift. Of course, there's no units on this, but now we are very wise climate scientists who are experts in heat waves, and so we definitely think that there's already a signal of heat waves changing. But I do think that we should be very purposeful in how we represent that to the media. We define heat waves as relative to the mean, right? And so if we increase the temperature on the Earth, but still compare it to average temperatures from before, of course, we're going to see more heat waves. But let's say we were changing our definition of what a heat wave is as we moved, then we would still have like the same number of events because the mean is now just different. So we're comparing it to different climatology. However, if the shape of the bell curve changes, that means that something in the dynamics of the atmosphere has also changed. So we're getting, for example, more high pressure systems that are just causing events more often. So like these events are no longer like in the 95th percentile, maybe now they're in the 70th percentile.
And is that happening? They're both.
I think that's a hard question to answer. I would say that the behavior that we're seeing so far is really well represented by just a shift in the mean. But to me, at least, that graph I showed on the previous plot showing that the intensity of the events is increasing a little bit faster than the mean, I think maybe complicates that picture. But I think most of the behavior is captured by a shift in the mean and not like a complete upheaval of how the atmosphere moves around. Okay, pretty much these are different RCP scenarios showing how these events are going to change with time. Obviously, 8.5 is the worst. Okay, quick summary. So, heat waves are extreme weather events, and they're defined relative to local conditions. You cannot compare what's going on in Alaska to the average temperature in Texas. You'll never have a heat wave in that case. And so it depends on where in the region you are and what the climatology in that region normally is. And then we spent a lot of time going over the different mechanisms of heat waves. The high pressure aloft that redirects precipitating storms away and keeps the area really dry. It can also lead to subsidence that induces adiabatic heating and drying. A clear sky with no clouds will allow more sunlight to get to the surface. Surface winds coming from the south can also bring hot air that can cause heat waves. If in the previous season there was less precipitation, that will also inhibit the soil's ability to cool. And then we also talked about how subsidence inhibits convection, and that will keep the winds from reaching the surface and then keep the soil from evaporating. We derived the wet bulb temperature and talked about how relative humidity and temperature changing in time will affect the human's ability to cool itself. And then we also talked about the heat wave statistics and how it's a little complicated, but with our thinking caps on, we can read these reports in a smart way. And basically the takeaway of this course is we do expect more heat waves in a warmer climate. There's pretty little uncertainty about that. I think that that's pretty clear. And the statistics are mostly captured by a shift in the mean and not so much a complete change in the atmospheric circulation. Okay, and that's it.